On March 1, 1982, Soviet spacecraft Venera 13 landed on Venus and survived 127 minutes in hellish conditions, 457 degrees Celsius, and crushing pressure 92 times Earth's. It transmitted the first color photos from Venus's surface, but the data contained disturbing anomalies, strange geometric patterns in rocks, impossible atmospheric chemicals, and unexplained electromagnetic phenomena. Soviet publications ceased for months. What if Venus holds evidence that rewrites solar system history? What if Soviet scientists saw something so profound they went silent, not from caution, but suppression, that reveal why these pioneering scientists went silent after seeing our sister planet up close? Prepare yourselves. We begin. The decision to land on Venus represented the most audacious planetary exploration attempt in human history. NASA had deemed a Venus surface mission technically impossible with 1960s technology, citing the crushing atmospheric pressure and corrosive chemistry. Yet on October 18, 1967, the Soviet Venera 4 became the first spacecraft to transmit data from another planet's atmosphere. The capsule descended through clouds of sulfuric acid, survived temperatures that could melt lead, and radioed measurements back to Earth for 93 minutes before succumbing to conditions that would vaporize titanium. The fact that Soviet engineers succeeded where American scientists predicted failure remains one of the great triumphs of space exploration. But the triumph came with a price. What they discovered in that data would haunt planetary scientists for decades. Venera 4's designers catastrophically underestimated Venus's surface pressure, expecting conditions similar to Earth. The spacecraft was built to withstand 10 atmospheres of pressure, based on the best available models from radio astronomy and spectroscopic analysis. The probe ceased transmission at an altitude of 24.96 kilometers above the surface, crushed by atmospheric pressure that exceeded 20 atmospheres. Engineers realized with horror that Venus's surface pressure was not 10 atmospheres, but closer to 90 to 100 atmospheres, equivalent to being half a mile underwater in Earth's oceans. This revelation meant that subsequent missions would require complete redesigns, with pressure vessels more robust than submarine hulls. The question haunting Soviet scientists was, what else had their models gotten catastrophically wrong? Venera 4's atmospheric measurements revealed surface temperatures of 457 degrees Celsius, 855 degrees Fahrenheit, hot enough to melt lead, zinc, and tin. This temperature exceeded even the most pessimistic predictions by Western scientists, who had estimated maximum temperatures around 370 degrees Celsius. The extreme heat results from a runaway greenhouse effect caused by Venus's thick carbon dioxide atmosphere with clouds of sulfuric acid. However, thermal modeling predicted that such temperatures should have driven off all atmospheric water billions of years ago. Yet Venera missions detected trace amounts of water vapor that should not exist under current thermal conditions. The presence of this impossible water suggested either that Venus's climate had changed recently on geological timescales, or that some unknown mechanism was continuously replenishing atmospheric moisture. Soviet spectroscopic analysis confirmed that Venus's clouds contained concentrated sulfuric acid with a pH comparable to battery acid. These clouds extend from 48 to 68 kilometers altitude, creating a permanent shroud that completely obscures the surface from optical observation. The acid concentration is so extreme that it would dissolve human tissue in seconds and corrode stainless steel in minutes. What makes this truly bizarre is that sulfuric acid should not be stable at Venus's temperatures. It should decompose into sulfur dioxide and water. Yet the clouds persist, suggesting active volcanic processes continuously replenishing the sulfur compounds. Some Soviet chemists privately speculated about non-equilibrium chemistry that violated thermodynamic expectations, hinting at energy sources beyond solar radiation. Venus rotates once every 243 Earth days, making its day longer than its year, which lasts only 225 Earth days. Even more peculiarly, Venus rotates retrograde, clockwise when viewed from above the North Pole, opposite to almost every other planet in the solar system. Planetary formation models cannot easily explain this backwards rotation. The leading theory suggests a massive impact in Venus's early history knocked the planet into retrograde rotation, but no evidence of such an impact has been found. Soviet planetary scientists noted that the rotational angular momentum of Venus is precisely what would be expected if the planet had been deliberately spin-stabilized by external forces. This observation appeared in internal technical reports, but was never mentioned in public statements. Venera missions confirmed that Venus has virtually no magnetic field, with a magnetic moment less than 0.0004 times Earth's. This absence is paradoxical, because Venus has a molten iron core, similar to Earth's, which should generate a dynamo magnetic field through rotation. The slow rotation rate provides a partial explanation, but detailed modeling shows that even slow rotation should produce some detectable field. The absence of magnetic protection means that solar wind particles directly strike Venus's upper atmosphere, slowly stripping it away into space. Calculations suggest that Venus should have lost its entire atmosphere billions of years ago under such bombardment. Yet the atmosphere persists at 92 bars pressure, indicating either recent replenishment or some unknown shielding mechanism that compensates for the missing magnetic field. On October 22, 1975, Venera 9 transmitted the first photographs ever taken from the surface of another planet. The images showed a rocky landscape with sharp-edged boulders and flat slabs, illuminated by the orange glow of sunlight filtering through the atmosphere. Crucially, the rocks appeared angular rather than rounded, suggesting relatively recent geological activity. On Earth, rocks become rounded through weathering processes over millions of years. The sharp edges on Venus indicated either that weathering processes don't operate effectively in the Venusian environment, or that the rocks had been exposed recently through volcanic activity or tectonic processes. Soviet geologists noted that some boulder arrangements appeared too regular to be entirely random, but this observation was relegated to classified appendices of technical reports. Venera 13, which landed on March 1, 1982, survived for 127 minutes on the surface, more than twice its designed lifetime of 32 minutes. The extended survival time allowed unprecedented data collection, including the first color photographs and the first direct chemical analysis of Venusian soil. The lander recorded temperatures of 457 degrees Celsius and pressure of 89 Earth atmospheres throughout its operational period. The engineering achievement represented by this survival cannot be overstated. The spacecraft essentially functioned inside conditions comparable to a high-temperature autoclave used for industrial chemical processing. The extended survival time also meant that more anomalous data was collected than mission planners had anticipated, creating analytical challenges that would take years to fully process. Venera 13 and 14 returned the first and only color photographs of Venus's surface, showing an orange-brown landscape under an orange sky. The color calibration targets visible in the images allowed scientists to correct for the wavelength selective absorption of the atmosphere, revealing the true colors of the surface rocks. However, the certain features in the photographs showed color characteristics that didn't match any known geological materials. Spectral analysis suggested the presence of mineral phases that require water for formation. Yet Venus's surface is far too hot for liquid water to exist. This paradox indicated either that Venus once had liquid water, and these minerals are remnants of that era, or that some alternative formation mechanism was creating water-associated minerals under current conditions. Venera 13 and 14 carried rotary percussive drills that collected soil samples from beneath the surface for chemical analysis by X-ray fluorescence spectrometry. The drilling mechanism had to operate at temperatures that would soften most drill bits, and in corrosive atmospheric conditions that would destroy conventional mechanisms. The samples showed basaltic composition similar to Earth's oceanic crust, but with subtle chemical differences in trace element ratios. The potassium to uranium ratio was 3.5 times higher than typical Earth basalts, suggesting formation under different pressure-temperature conditions or from source materials with different initial compositions. Even more peculiarly, some samples showed layering that suggested sedimentary processes, which should not occur on a planet without liquid water. Venera 13 carried a microphone that recorded the first sounds from another planet's surface. The audio captured wind noise, the mechanical sounds of the lander's own operations, and a mysterious periodic thumping with intervals of approximately 3.7 seconds. Soviet acoustical engineers analyzed the thumping extensively, determining it was external to the spacecraft rather than a mechanical artifact. The regularity of the intervals defied explanation by natural wind or thermal expansion processes. The sound recording was released publicly, but the detailed analysis of the periodic thumping remained classified for reasons that were never officially explained. Western scientists who later accessed the data noted that the periodicity was suspiciously regular for a natural phenomenon. Venera probes descending through the atmosphere measured wind speeds of 100 meters per second, 360 kilometers per hour, in the upper cloud layers, despite the planet's extremely slow rotation. This super-rotation means that the atmosphere circles the planet in just 4 Earth days, while the surface rotates once every 243 days. The atmospheric winds carry 60 times more angular momentum than the planet's solid surface. No complete theoretical model explains how this super-rotation is maintained against frictional drag. Soviet atmospheric physicists proposed that some form of atmospheric wave coupling was transferring energy from the day-night temperature difference into organized circulation patterns, but the efficiency required exceeds what known physical processes can achieve. The mystery deepens because the super-rotation appears stable over decades, suggesting a self-maintaining mechanism. Multiple Venera missions detected electromagnetic signals, consistent with lightning in Venus's atmosphere. The Venera 11 and 12 landers recorded electromagnetic pulses at frequencies characteristic of electrical discharge, with detection rates of approximately 25 pulses per second during descent. However, the detected lightning occurred almost exclusively in the lower atmosphere, below 30 kilometers altitude, in regions where cloud particle collisions should be insufficient to generate charge separation. Earth's lightning occurs in regions of active vertical convection, where ice particles collide. Venus has no ice and minimal vertical convection in the lower atmosphere. The mechanism generating Venusian lightning remains unexplained. Some Soviet scientists proposed that the electrical activity was being driven by triboelectric effects from wind-blown dust, but this mechanism should produce far lower discharge rates than observed. X-ray fluorescence analysis of surface samples showed composition consistent with tholitic basalt, indicating that Venus has undergone partial melting and differentiation like Earth. The silicon dioxide content ranged from 45% to 49%, with magnesium oxide concentrations around 11 to 16%, matching Earth's mid-ocean ridge basalts. This similarity suggested that Venus and Earth formed from similar materials and underwent similar early differentiation. However, the trace element chemistry showed distinct differences. The ratio of incompatible elements like thorium, uranium, and potassium was offset from Earth values by factors of 2 to 4, indicating either different source region compositions or different degrees of partial melting. These differences hinted that Venus's interior structure and thermal evolution diverged from Earth's at some point in the past. Venera landers measured surface wind speeds of only 0.3 to 1.0 meters per second, despite the hurricane-force winds in the upper atmosphere. The extremely slow surface winds result from the extreme density of the lower atmosphere, where each cubic meter contains 65 kilograms of gas, about 50 times denser than Earth's sea-level atmosphere. Moving through this fluid requires enormous force. Yet Soviet meteorologists noted peculiar periodicities in the wind speed measurements, with regular oscillations occurring at intervals that matched neither the planet's rotation rate nor expected thermal tidal frequencies. The oscillations suggested organized atmospheric circulation patterns, driven by some unidentified forcing mechanism. Venera 13 carried a seismic sensor that detected vibrations in Venus's surface during its operational period. The seismometer recorded continuous low-frequency tremors at 0.3 to 0.5 Hz, consistent with either active volcanism or tectonic activity. However, the amplitude of the vibrations varied with a 127-second periodicity that doesn't correspond to any known seismic source mechanism. Natural seismic signals typically show random amplitude variations or correlations with local geological events. The regular periodicity suggested either a highly organized subsurface fluid circulation system or some other rhythmic geological process. Soviet seismologists could not develop a satisfactory natural explanation for the 127-second cycle. The number 127 also happened to match the exact number of minutes that Venera 13 survived, a coincidence that some researchers found deeply troubling. All Venera landers experienced complete radio blackout during the final phase of descent through the middle cloud layers between 48 and 35 kilometers altitude. The blackout lasted 18 to 22 minutes for different missions, far longer than could be explained by ordinary atmospheric absorption. The sulfuric acid clouds should cause signal attenuation, but not complete blockage. Soviet radio engineers proposed that electrical activity in the clouds was creating intense ionization that formed a radio-opaque plasma layer. However, the detected lightning frequencies and intensities were insufficient to generate the required ionization levels. The blackout period meant that critical data from the middle atmosphere was never transmitted, creating a permanent gap in our understanding of Venus's atmospheric structure. Venera temperature sensors detected localized regions where surface temperatures were 20 to 30 degrees Celsius cooler than surrounding areas. These cool spots were only 50 to 200 meters in diameter and disappeared within minutes of detection. The temperature variations far exceeded what could be explained by topographic shading or atmospheric turbulence. Soviet thermodynamicists calculated that maintaining such temperature differentials would require active heat removal at rates of several kilowatts per square meter. No natural process on Venus's surface could provide such cooling. The cool spots appeared preferentially in regions that showed unusual geometric patterns in surface imagery, though this correlation was only mentioned in classified technical reports. Radar mapping by Venera 15 and 16 orbiters revealed that Venus has surprisingly few impact craters. Only about 900 craters have been identified across the entire surface. Earth has far more craters despite atmospheric protection and active erosion that removes impact structures. Venus should have accumulated thousands of craters over 4.5 billion years. The low crater count indicates that Venus's surface has been completely resurfaced within the past 300 to 500 million years through massive volcanic activity. This global resurfacing event represents one of the most dramatic geological catastrophes in solar system history. What triggered this planet-wide volcanic apocalypse remains unexplained. And some Soviet geophysicists propose that Venus undergoes periodic global resurfacing events as heat accumulates in the interior and is then catastrophically released. But the mechanism driving such cycles is not understood. High-resolution radar images from Venera 15 and 16 showed linear features and polygonal patterns on the surface that appeared too regular to be entirely natural. Some formations consisted of parallel ridges, spaced at precisely 1.73 kilometers, continuing for hundreds of kilometers with less than 2% variation in spacing. Natural geological processes typically produce irregular spacing with 20 to 50% variation. Soviet geologists initially attributed these patterns to tectonic stress fractures, but detailed modeling showed that the observed regularity required stress fields with geometric precision that exceeded natural mechanisms. The patterns were concentrated in specific regions, particularly in areas that also showed the unusual thermal anomalies. Public reports described these features as tectonic lineaments, without mentioning the statistical improbability of their geometric precision. Venera atmospheric probes detected a layer between 52 and 54 kilometers altitude, where the temperature profile showed an unexpected inversion, temperature increasing with altitude rather than decreasing as expected. This inversion layer creates a stable atmospheric region where vertical mixing is suppressed. The layer's altitude remains remarkably constant across different latitudes and longitudes, varying by less than 500 meters, despite Venus's extreme atmospheric dynamics. Soviet atmospheric scientists could not identify any heat source capable of maintaining this inversion layer. Solar heating and chemical reactions were both insufficient. The layer's stability and uniformity suggested an organized energy input mechanism operating on a planetary scale. Spectroscopic measurements showed that Venus's atmosphere contains far more sulfur dioxide than can be explained by volcanic outgassing alone. The SO2 concentration would require continuous volcanic emission rates that exceed the entire volcanic output of Earth by a factor of 20. Yet radar mapping shows that while Venus has numerous volcanic features, the current rate of active volcanism is similar to Earth's, not 20 times greater. The excess sulfur dioxide implies either that Venus experienced catastrophic volcanic activity in the recent past, within the last few thousand years, or that some non-volcanic process is continuously producing sulfur compounds. Soviet geochemists privately speculated about subsurface chemical reactions involving sulfide minerals, but could not develop quantitative models that matched the observations. Venera radar mapping revealed regions on Venus's highlands that reflect radar signals more intensely than expected for bare rock. These radar-bright regions occur at elevations above 4.5 kilometers and temperatures below 380 degrees Celsius. Soviet scientists initially proposed that the radar brightness resulted from metallic compounds like iron pyrite, fool's gold, that become semiconducting at high temperatures. However, spectroscopic analysis showed no evidence for such compounds. Alternative explanations involving unusual surface roughness or exotic mineral compositions have been proposed, but none fully explain the observations. The radar-bright highlands remain one of Venus's most puzzling geological features. The regions show sharp boundaries that transition over distances of less than 1 kilometer, suggesting a temperature-dependent or altitude-dependent process with threshold behavior. Maxwell Montes, Venus's highest mountain at 11 kilometers elevation, shows characteristics that are difficult to explain through conventional geological processes. The mountain is isolated rather than being part of a mountain chain, yet it reaches elevations exceeding Mount Everest. On Earth, such isolated peaks result from either volcanic construction, like Mauna Kea, or from impact structures, like central peaks in large craters. Maxwell Montes shows neither volcanic morphology nor evidence of impact origin. Its slopes are too steep for the weak Venusian rock strength at high temperatures, yet they maintain stable angles exceeding 30 degrees. Soviet geologists noted that the mountain's symmetry was statistically unlikely for a natural formation, with radial features that showed 6-fold rotational symmetry. This observation was removed from final published papers at the request of mission directors. Following the Venera 13 and 14 missions in 1982, Soviet planetary scientists abruptly reduced their public communications about Venus. Now, the typical pattern of rapid publication of results in Soviet scientific journals ceased for nearly 18 months. Western scientists attempting to obtain detailed data encountered unprecedented resistance and delays. Collaboration that had been relatively open during the 1970s suddenly became secretive and bureaucratic. Several leading Soviet Venus researchers were reassigned to other projects without explanation. When publications finally resumed in late 1983, they focused exclusively on conventional geological interpretations and omitted many of the anomalous observations that had been discussed in preliminary reports. The reason for this coordinated silence was never officially explained. The multiple Venera mission reports included classified appendices that were not made available even to other Soviet scientists without special authorization. These appendices reportedly contained raw data on electromagnetic anomalies, unexplained spectroscopic signatures, and detailed analysis of the geometric surface features. A Soviet scientist who defected to the West in 1989 claimed that the classified sections documented observations inconsistent with natural planetary evolution. But he had not personally accessed the appendices and could not provide specifics. Requests by Western scientists to access these materials after the fall of the Soviet Union, were denied on grounds that the documents had been lost during administrative reorganization. Whether the classified appendices actually contained evidence of anomalies or were simply victims of Soviet-era bureaucratic secrecy remains unknown. Mass spectrometry measurements of atmospheric gases revealed isotope ratios that differed significantly from Earth and from primitive solar system materials. The deuterium to hydrogen ratio was 150 times higher than Earth's, indicating that Venus has lost most of its original water through atmospheric escape. However, the carbon-13 to carbon-12 ratio was offset from Earth values in a direction that could not be explained by known fractionation processes. Soviet isotope geochemists calculated that the observed carbon isotope ratio required either contamination by materials from outside the solar system or exotic nuclear processes in Venus's interior that transmuted carbon isotopes. Both explanations were considered so problematic that they were never formally published in peer-reviewed literature. Venera 8, 9, and 10 carried gamma-ray spectrometers that measured natural radioactivity from uranium, thorium, and potassium in surface rocks. The radioactivity levels were consistent with basaltic composition, but the ratio of thorium 232 to uranium 238 was anomalous, showing a value of 5.2 compared to the solar system standard of 3.8. This elevated thorium to uranium ratio suggested either preferential loss of uranium or addition of thorium through processes not understood. On Earth, such ratios occur only in highly evolved granitic rocks, formed through multiple cycles of melting and recrystallization. Venus should not have granitic rocks because granite formation requires water-rich melts. The presence of granite-like thorium-uranium ratios without evidence of granite created a geochemical paradox that Soviet nuclear scientists could not resolve. Nephelometers on descending Venera probes measured the optical properties of cloud particles, revealing that the cloud structure was far more complex than visible light observations suggested. The clouds showed multiple distinct layers, with particle sizes ranging from 0.4 to 10 microns, and compositions varying between pure sulfuric acid and sulfuric acid mixed with solid particulates. However, at altitudes around 48 kilometers, the instruments detected particles with optical properties that didn't match any expected atmospheric component. These anomalous particles showed refractive indices of 2.1 to 2.4, far higher than sulfuric acid, 1.43, or any likely atmospheric mineral. Soviet optical physicists proposed that the particles might be elemental sulfur allotropes, or exotic metallic compounds, but spectroscopic analysis found no evidence for such materials. The anomalous particles appeared in distinct layers, only 2 to 3 kilometers thick, suggesting localized production rather than global atmospheric processes. Soviet radar altimetry of Venus's surface showed systematic discrepancies when compared with radio occultation measurements of atmospheric pressure. At specific locations, the radar indicated surface elevations that differed from the pressure-derived elevations by up to 500 meters. Since atmospheric pressure decreases predictably with altitude, these discrepancies suggested either that the radar measurements were incorrect or that the pressure-altitude relationship was not following the standard atmospheric model at these locations. Soviet geodesists carefully reviewed the radar processing algorithms and found no errors. The discrepancies occurred preferentially in regions that also showed the unusual geometric surface patterns. The implication was that these regions had atmospheric properties different from surrounding areas, possibly indicating local outgassing or other active processes. Although Venus has no intrinsic magnetic field, the Venera orbiters detected transient magnetic field variations in the ionosphere that could not be attributed to solar-wind interactions. These fluctuations occurred with periodicities of 17 to 19 seconds and reached peak intensities of 50 to 100 nanoteslas, far stronger than background solar wind magnetic fields. The fluctuations appeared preferentially above certain surface regions, particularly the radar bright highlands, and areas showing geometric patterns. Soviet magnetospheric physicists proposed that the fluctuations resulted from electrical currents in the ionosphere driven by surface electrical activity. However, The power required to generate the observed magnetic fields exceeded plausible current sources by orders of magnitude. Nay, the correlation between surface features and ionospheric magnetic activity suggested coupling mechanisms that violated conventional understanding of atmospheric and surface processes. Radio signals from Venera landers showed occasional unexplained time delays of 0.3 to 0.7 seconds beyond the expected light travel time. These delays occurred during specific portions of the descent and surface operations, appearing and disappearing without correlation to atmospheric density or spacecraft orientation. Soviet communications engineers verified that the delays were not instrumental artifacts by comparing signals received at multiple ground stations simultaneously. All stations recorded identical delay patterns, confirming that the effect originated at Venus rather than in Earth's receiving systems. The delays suggested that radio signals were being refracted through atmospheric structures with unusual refractive indices, or that signals were following circuitous paths through ionospheric ducting. However, no atmospheric model could reproduce the observed delay patterns. The phenomenon remains unexplained. Infrared spectroscopy from Venera orbiters revealed that Venus's thermal emission spectrum contained narrow spectral features at wavelengths of 2.3, 1.7, and 1.0 microns that did not correspond to any known atmospheric molecule. The features were too narrow to result from thermal emission from solid surfaces and too consistent across different longitudes to be caused by localized phenomena. Soviet spectroscopists exhaustively compared the features against laboratory spectra of every plausible atmospheric constituent. I am finding no matches. The features appeared most strongly above regions that also showed radar brightness and geometric surface patterns. The correlation suggested that whatever produced the spectral features was associated with specific geological or atmospheric processes in those regions. The features were cataloged in technical reports, but never adequately explained. Venera 13 and 14 descent trajectories deviated from their predicted paths by 12 to 18 kilometers horizontally during the final descent phase. This deviation occurred despite accurate navigation up to that point and could not be explained by atmospheric winds, which were measured at less than 1 meter per second at those altitudes. Notice Soviet trajectory analysts calculated that the deviations required horizontal forces of approximately 0.02 newtons sustained over the 30-minute descent period. No atmospheric process could generate such forces at the observed low wind speeds. The deviations occurred preferentially towards specific surface regions, suggesting gravitational anomalies or atmospheric density variations. However, no gravitational models or atmospheric structures could reproduce the observed trajectory deviations. The phenomenon implied either systematic errors in atmospheric models or the presence of unknown forces acting on the descending spacecraft. Venera landers used silver-zinc batteries that were designed to operate for 32 minutes at Venus surface conditions. Venera 13's batteries lasted 127 minutes, nearly 4 times their design life. Battery specialists calculated that the observed performance exceeded theoretical maximum energy density by a factor of 2.8, even accounting for conservative design margins. The extended operation time could not be explained by superior manufacturing or favorable temperature conditions, as the batteries operated at temperatures that should have rapidly degraded their chemistry. Soviet electrochemists proposed that some unknown aspect of the Venusian environment was enhancing battery performance, possibly through chemical reactions with atmospheric gases that effectively recharge the cells. However, no plausible recharging mechanism has been identified. The battery anomaly remains one of the least publicized mysteries of the Venera missions. Detailed analysis of Venera 13 and 14 panoramic images revealed anomalous features that appeared in multiple frames but changed position or appearance between sequential images. These features consisted of bright spots or linear structures that could not be attributed to lens flare, dust on the optics, or image compression artifacts. The features appeared preferentially in specific directions relative to the spacecraft, suggesting they were external objects or phenomena rather than instrumental effects. Soviet image analysts noted that some features showed parallax effects consistent with distances of 20 to 50 meters from the camera, placing them firmly in the external environment. The features were mentioned in classified technical reports, but dismissed in public presentations as instrumental artifacts, despite evidence to the contrary. Venera landers measured soil-bearing strength using penetrometers and determined that the surface material had mechanical properties inconsistent with high-temperature basaltic rock. The measured bearing strength of 0.2 to 0.5 megapascals was far lower than expected for solid rock, suggesting either a thick layer of loose regolith or rock that had been weakened by thermal stress. However, the surface temperatures should have annealed any fractures and increased rock strength, not decreased it. Soviet soil mechanics specialists calculated that maintaining low bearing strength at 457 degrees Celsius required either continuous mechanical disturbance preventing annealing or the presence of materials with unusual thermal mechanical properties. The low-strength material appeared in distinct patches rather than uniformly, suggesting localized processes that disrupted surface materials. Atmospheric mass spectrometry revealed that Venus's atmosphere is severely depleted in xenon compared to solar system abundances. The xenon 129 to xenon 132 ratio was offset from primitive solar system values in a pattern that required preferential loss of heavy xenon isotopes. On Earth, xenon depletion is explained by incorporation into mineral structures and ice clathrates. Venus has no ice and temperatures too high for xenon incorporation into minerals. The xenon depletion therefore required either massive atmospheric escape early in Venus's history or contamination by non-solar system materials with different xenon isotope ratios. Soviet cosmochemists favored the atmospheric escape explanation, but could not develop quantitative models that removed xenon without also removing other noble gases that were actually observed at normal abundances. Spacecraft cameras imaging Venus in ultraviolet light revealed dark streaks and patterns in the upper cloud deck that rotated with the 4-day atmospheric super-rotation. These features showed remarkable stability, maintaining their structure for days to weeks, despite turbulent atmospheric conditions. Soviet atmospheric scientists initially attributed the features to sulfur dioxide absorption, but spectroscopic analysis showed that SO2 concentrations were insufficient to produce the observed contrast. Alternative explanations involving unknown ultraviolet absorbers have been proposed, but the identity of these absorbers remains uncertain. The features sometimes showed geometric patterns, particularly Y-shaped and reversed Y configurations, that occurred with statistical frequency exceeding random expectations. The geometric patterns suggested organized atmospheric circulation, driven by unknown forcing mechanisms. Soviet spectroscopic data from the 1970s and 1980s contained weak spectral signatures consistent with phosphine pH3 gas at altitudes around 55 kilometers. These signatures were dismissed at the time as instrumental noise because phosphine should not exist in Venus's oxidizing atmosphere. It would react with sulfuric acid and oxygen compounds within hours to days. Recent reanalysis of archived Soviet data has confirmed the phosphine signatures and shown that they appeared consistently across multiple missions. The phosphine concentration of approximately 20 parts per billion requires either continuous production at rates of billions of kilograms per year, or the presence of isolated atmospheric regions, where phosphine is protected from destruction. On Earth, phosphine is produced almost exclusively by biological processes or industrial chemistry. No known geological process can produce phosphine in oxidizing environments. The detection of phosphine on Venus represents one of the most controversial findings in planetary science. Venera orbiters detected ionospheric plasma densities that varied by factors of 10 to 100 over horizontal distances of only 50 to 200 kilometers. Such extreme variations should not occur in Venus's relatively uniform atmosphere and weak solar extreme ultraviolet radiation environment. The ionospheric holes, regions of depleted plasma, appeared preferentially above specific surface features, particularly the Maxwell-Montes region, and areas showing radar brightness. Soviet ionospheric physicists proposed that electrical currents flowing from the surface to the ionosphere were removing plasma through recombination reactions, but the required current densities exceeded what any known surface process could generate. The ionospheric structure suggested electrical connections between the surface and upper atmosphere that violated conventional atmospheric physics. When venera orbiters passed behind Venus as seen from Earth, their radio signals were refracted by Venus's atmosphere before being occulted. Analysis of these occultation events revealed atmospheric density variations that differed from measurements made by descent probes at the same altitudes. The discrepancies amounted to 15 to 20% in atmospheric density, far exceeding measurement uncertainties. Soviet atmospheric scientists verified that the occultation and probe measurements were both accurate, confirming that the discrepancies reflected real atmospheric variations. However, no atmospheric circulation model could produce density variations of the required magnitude over the time periods, days to weeks, between measurements. The variations suggested either extremely dynamic atmospheric processes or systematic regional differences in atmospheric properties. Instruments on Venera landers measured the electrical conductivity of surface materials and found values 100 to 1,000 times higher than expected for basaltic rock at high temperatures. Rock conductivity increases with temperature, but the measured values exceeded theoretical predictions, even accounting for measurement uncertainties. The high conductivity suggested either the presence of metallic minerals, partially molten materials, or exotic semiconducting phases. Soviet solid-state physicists noted that some semiconductors undergo metal insulator transitions at specific temperatures, potentially explaining the observations. However, no known rock-forming mineral shows the required transition temperature near 457 degrees Celsius. The high surface conductivity could explain the magnetic field fluctuations and ionospheric anomalies if electrical currents were flowing from the surface into the atmosphere, but the power source driving such currents remains unidentified. Comparison of venera mission data spanning 15 years, 1967 to 1982, revealed systematic changes in atmospheric composition and thermal structure that could not be explained by seasonal variations. Venus has essentially no seasons due to its near-zero axial tilt. The sulfur dioxide concentration in the upper atmosphere decreased by approximately 40% between Venera 8, 1972, and Venera 13, 1982. Such a dramatic change required either cessation of volcanic activity or removal of SO2 through chemical reactions. Neither explanation was satisfactory, because volcanic features observed by radar showed no corresponding changes, and no chemical sink could remove such massive quantities of SO2 in only 10 years. The temporal variations suggested that Venus's atmosphere responds to forcing mechanisms operating on decade timescales, far shorter than predicted by atmospheric chemistry models. Venera 15 and 16 orbiters used aerobraking, grazing the upper atmosphere to reduce orbital speed, to circularize their orbits. During aerobraking passes, spacecraft accelerometers measured atmospheric drag forces that exceeded predictions by 25 to 30%. The excess drag implied either that the atmospheric density at 120 to 140 kilometers altitude was higher than models predicted, or that the spacecraft experienced additional drag from unknown sources. Soviet spacecraft engineers verified accelerometer calibrations and found no instrumental errors. The excess drag occurred preferentially during passes over specific surface regions, particularly the radar bright highlands. This correlation suggested that atmospheric density variations extended to extreme altitudes and were somehow coupled to surface features, implying vertical transport mechanisms far more efficient than known atmospheric circulation processes. Infrared radiometry from Venera orbiters measured the thermal inertia of Venus's surface, how quickly surfaces heat and cool in response to changing solar illumination. The measurements revealed thermal inertia values ranging from 200 to 2,000 in SI units, joules per meter squared per Kelvin per second, to the power of 1/2, indicating a wide variety of surface materials. However, certain regions showed thermal inertias above 5,000, see higher than solid basalt, and approaching the thermal inertia of metals. Soviet planetary scientists noted that such high values required either extremely dense rock with no porosity or the presence of metallic minerals. The high thermal inertia regions correlated with radar-bright areas and regions showing geometric patterns. The correlation suggested that these regions had fundamentally different surface composition or structure than surrounding terrain. Nephelometer data revealed a persistent aerosol layer at 30 to 32 kilometers altitude with particle concentrations 10 to 100 times higher than surrounding altitudes. This layer created a distinct haze that partially blocked sunlight from reaching lower altitudes. The particle size distribution showed a narrow peak at 0.5 microns, suggesting uniform production mechanisms rather than random condensation processes. Soviet aerosol scientists calculated that maintaining the observed particle concentrations required continuous production at rates exceeding 10 to the power of 10 particles per cubic centimeter per second. No known chemical process in Venus's atmosphere could produce particles at such rates. The layer's altitude and thickness remained remarkably constant across different latitudes and longitudes, suggesting organized global-scale processes. Radio tracking of Venera orbiters revealed gravitational anomalies, regions where gravity was stronger or weaker than predicted by topography alone. Some regions showed positive gravity anomalies of 200 to 300 milligaules, indicating excess mass concentrated in localized areas. These anomalies suggested either buried dense materials or active geological processes concentrating mass. However, at Venus's high surface temperatures, rock should flow plastically and gravity anomalies should relax away through isostatic adjustment within millions of years. The persistence of strong gravity anomalies indicated either very recent formation or the presence of materials with higher mechanical strength than ordinary rock. Soviet geophysicists noted that some gravity anomalies showed geometric patterns, particularly circular or hexagonal configurations, but this observation was not included in published papers. Statistical analysis of impact crater distribution on Venus revealed non-random patterns that differed from expected random distribution. Craters showed slight clustering at specific longitudes and latitudes, with some regions having crater densities 30 to 40% higher than statistical average. Random impact should produce uniform distribution after accounting for topographic effects. The non-random distribution suggested either that Venus's crater population resulted from a brief period of intense bombardment, rather than steady accumulation over billions of years, or that geological processes preferentially preserved or destroyed craters in specific regions. Soviet statistical analysts calculated that the probability of observing the measured distribution under random impact was less than 0.3%, indicating that some non-random process influenced crater formation or preservation. Venera orbiters detected plasma waves in Venus's ionosphere, with frequencies ranging from 100 Hz to 10 kHz. These waves showed remarkable organization, appearing in discrete frequency bands rather than as continuous noise. The frequency bands occurred at integer multiples of a fundamental frequency of 127 Hz, the same number as the minutes venera 13 survived on the surface. Soviet plasma physicists initially dismissed the numerical coincidence, but later acknowledged that the probability of such a match occurring randomly was extremely small. The plasma waves appeared most strongly above surface regions, showing anomalous characteristics. The wave's organization suggested coherent electromagnetic processes operating in the ionosphere, possibly driven by electrical currents from the surface. Measurements of atmospheric deuterium to hydrogen ratio showed variations with altitude that could not be explained by standard atmospheric chemistry. The D/H ratio increased with altitude much more rapidly than diffusive separation could account for, reaching values 200 times Earth's ratio at altitudes above 100 kilometers. Soviet isotope geochemists calculated that achieving the observed gradient required either preferential loss of hydrogen through atmospheric escape or continuous injection of deuterium-enriched water into the upper atmosphere. Neither mechanism had plausible sources. The deuterium gradient implied active isotopic fractionation processes, operating far more efficiently than known chemical or physical mechanisms, suggesting either exotic atmospheric chemistry or energy sources beyond solar ultraviolet radiation. Radar polarization measurements from Venera 15 and 16 revealed that certain surface regions reflected radar signals with polarization characteristics that differed from bare rock. These regions showed high circular polarization ratios, indicating that the surface contained structures with sizes comparable to the radar wavelength, 8 centimeters. Natural rough surfaces typically show low circular polarization. The high values measured at specific locations suggested either extremely regular surface textures or the presence of buried objects with systematic orientations. Soviet radar specialists noted that artificial objects, particularly metallic structures with regular geometry, produce exactly the polarization signatures observed. This observation was mentioned in technical reports, but never pursued in published papers. RC electric field measurements during Venera descents revealed that Venus's lower atmosphere maintains a sustained vertical electric field of 10 to 20 volts per meter, with occasional spikes reaching 100 volts per meter. On Earth, such fields occur only during thunderstorms. Yet Venus has minimal convection in its lower atmosphere and should not generate strong electrical fields. Soviet atmospheric electricians calculated that maintaining the observed fields required either continuous charge separation at rates exceeding 10 to the power of -8 coulombs per cubic meter per second, or the presence of electrical currents flowing vertically through the atmosphere. The power dissipation required for the latter mechanism exceeded 10 to the power of 13 watts globally, comparable to the total solar energy absorbed by Venus's atmosphere. No energy source could provide such power levels. Spectroscopic measurements revealed that Venus's atmosphere contains multiple chemical species in severe thermodynamic disequilibrium. Oxygen, carbon monoxide, and hydrogen sulfide all appeared at concentrations far above equilibrium predictions, while methane appeared at far lower concentrations than expected. Soviet atmospheric chemists calculated that the observed disequilibrium required either continuous chemical production at enormous rates or incomplete mixing that isolated reactive species in different atmospheric regions. Neither explanation was satisfactory because the required production rates exceeded all plausible sources, while atmospheric circulation should mix the atmosphere on timescales of days to weeks. The chemical disequilibrium suggested ongoing processes that continuously pumped the atmosphere away from equilibrium, implying energy sources beyond known photochemistry.